Hey friends, this is Derek from TCI, and this is part 2 of my networking video series, and this chapter is about switches. Okay, before I start this chapter, I'd like to cover a few things that are going to be a big deal as you go through all the chapters that I lay out. One, you're going to learn a ton of acronyms, so you might need to start making a list. I'm going to keep a running total of them on my video so that you can see them, and I'll try to put them in the description as well. It's a lot to ask for new students to learn all the concepts and remember all of the three-letter acronyms that they're going to encounter. It's part of the computer world in general. You're gonna get used to it. It'll slowly seep in. Don't get too hung up on it. As much as possible, I'll try not to say the acronym when I could say the actual full word. But broadly speaking, when you're out in the field working at a job with your colleagues, everyone's going to toss around acronyms like crazy. So just try and roll with it. If you don't know what they are, type them into Google, you'll find it. The other thing that I want to cover is that when I'm giving you the breakdown of how these things function, keep in mind that there's always going to be an exception. There are times when we break the rules to solve problems. So I'm going to give you broad rules that these things live by, but don't think of it as absolutely immutable. There's going to be a lot of times, and you may have already experienced them before you watch this video, where you hear me say, here's the rule, but then you've already heard, there's times we don't do that. That's perfectly normal. We just need to keep an open mind and an inquisitive nature, and remember that there's more to learn. Every time you scratch the surface, there's more to learn under there, and there's more to learn under that. The lowest I'm going to talk about today is the Ethernet frame, but you can get real deep. There's link integrity tests. There's all kinds of pulses that we could learn about, the exact engineering methods that they use to send the electrical signals down the wire. You could really get lost down the rabbit hole, and that's perfectly fine. Don't feel like you've ever mastered it, and don't let anyone get you down when they tell you like, oh, but what about this? What about that? What about it? We're going to learn. Don't you worry. We'll get there. But as you're starting out, you're a new student, start with the basics, and then we'll expand on those as we go. All right. As I covered before in the previous video, switches are a basic networking device that you use to pass messages between computers. They come in many shapes and sizes, so as part of this training, I'm going to try to meld the physical nature of the network that we're building with the theoretical or logical nature of the network as we learn it. Let's start with something extremely basic that everybody needs to know, and that's how to identify a switch when you see one. So as you see here on the table, I've got a stack of various types of switches. I've got my 5-port, my 8-port, my 24, and my 48. Switches come in all shapes, flavors, sizes, colors, and arrangement of ports that you could ever imagine. And being able to tell when you're looking at one is really important. Let me give you an example that I run into a lot when I'm talking to someone over the phone and trying to help them out. This is not a switch, but you could be forgiven for thinking that it might be. It looks a lot like one. It's got the ports, just like the switches do on the stack over here. However, this is a router. So in order to identify these, always take a close look at the labels that are below or above each of these ports and try to read off or look for identifying marks. On a router, ports are typically labeled WAN, LAN, or ETH for Ethernet. For some specific variety of firewall or router combinations, they may say X0, X1. Switches by and large just say port 1, 2, 3, 4, 5, and that'll be a very simple device. If you get the sense that it's got labels indicating it has more features than just message passing, you may be looking at a router, a firewall, or some other device. Now, as we spend more time doing labs and experimenting with the switches, etc., you're going to eventually get a handle on it. What I want to have happen is that you know exactly what it is because you've tested it with your own two hands in a home lab environment or a work lab environment, etc. When you're learning this purely theoretically, your only exposure to the switches might just be in a simulation. And if that's the way you learn, you won't be any good if I stick you in the data center and I tell you to build this out. You'll have never set hands on it, and it won't be super useful in a training environment for me to not show you physically how these things work. So let me start here with the smallest switch. And I'll do most of my talking with this basic one. Just keep in mind, the more ports that you have, the bigger your network. But in terms of functionality, all of these ones that are here on the table work the same way. They pass messages back and forth from one port to the other ports. It doesn't matter where you plug a computer in. So I've got a little HP mini computer here, and on the back of it, I have a network port. When you connect things to your switches, you're going to be using a cable that looks like this. There's a lot of different names for it. The official designation is going to be the 8 position, 8 conductor RJ45. But most of the time, I just call it a patch cord or a Cat6 cord. The reason we call it a patch cord is you're going to use it to simply patch in, which is the activity that I've just done. Whenever I plug in something between a device and a switch, that's called patching. Now I'm going to add my mini tower to the switch as well. So I'm going to patch that in to my switch. And it doesn't matter where on the switch I've patched in, these two computers can now pass messages through the patch cord or the Cat6 cable, and they're able to communicate. I can pass files between them, text messages, whatever my application allows me to do. Now, before I go any further explaining how switches communicate, I want to talk a little bit about that port that I'm patching into on the back of this computer. I have a computer motherboard here that I've removed from its case so that you can see the circuitry. These are the RJ45 ports that are available on this motherboard. And if you look closely, there's associated circuitry on the board behind each of these ports. This is the circuitry that converts electrical signals to and from information and then moves it into your computer's memory. Your RJ45 port and all of the associated buffers, circuitry, transmitters, receivers, etc. that are on your motherboard are collectively referred to as your network interface card, or NIC. A computer can have more than one NIC, and if you need to add one, you could use something as simple as a USB to Ethernet adapter. This adds a NIC to a computer that needs one. Perhaps you've broken the pins, or you have a wireless-only device. If you add with the USB expansion, you get another NIC. A computer with multiple NICs can be plugged into more than one network. I'll talk a bit more about this in a future video, as that's slightly more advanced than what we're going for right now. I'm just trying to introduce you to the basic concepts in this video. When you patch your computer into a switch, one of the things you'll see happen as a result is that a green light will turn on. This is called the link light, and this shows that there's been an established communication between the switch and my device. It's not a guarantee that information is able to pass. There could be still something wrong with my software, or possibly I might have a bad cable, and the link light can still come on in certain circumstances. But for the most part, patching in a store-bought device into a store-bought switch with store-bought cables, nothing that you've made yourself, is a pretty good indicator that we now have communication to the network. So how does your switch know which computer is plugged into which port when it comes time to pass messages between them? As it happens, your network interface card has a serial number burned into it at the factory that never changes. This serial number is called the Media Access Code. It is said shorthand as the MAC. Your MAC address is a code number or serial number that your switch uses to track which computer is in which port. When your computers pass messages between each other, they stamp the message with their MAC address. This allows the switch to learn which port has which MAC address in it, and when it needs to forward a message to a particular MAC address, it knows which port to forward that message into. As messages pass back and forth between the computers, the switch builds what we call a MAC address table. It is a list of all the MAC addresses or serial numbers that the switch has learned and which port they are in. On a small network, it'll just be a few entries, and on a big network, it could be thousands. Each computer's MAC address should be unique within the switch. If the same MAC address exists on more than one port within the MAC address table, you may not receive the frames as you're intending to. In addition to each of the MAC addresses needing to be unique, there is a reserved MAC address where every single value is set to FF. If the destination of a particular frame is set to all Fs, then what will happen is the switch will broadcast to all available ports that frame. This is one way that computers on the network learn about each other's presence. They send out periodic broadcasts that help them build a list of available computers on the network. The switch will use answers to any broadcasts to help it build its MAC address table. So far, I've been referring to the communications between computers as messages, but the proper name is frame. Ethernet frames are what switches operate on. They pass frames down the patch cords in the form of electrical signals. Ethernet frames have a very specific format. There's a destination MAC address, and there is a source MAC address. Whenever we send a frame between two computers, the switch needs to know who the target is and who the source is. That's so we can deliver the message to the target and then deliver the answer back to the source. Ethernet frames also have a tag field, but I'll talk about that in a future video as it's a slightly more advanced concept. It then has an ether type field. In some cases, this designates the length of the amount of information we're passing inside of this frame, or it can be alternatively used to tell the switch or receiving device what the content of the payload is. The following information is then the payload. The minimum size of your payload is 64 bytes. The maximum size is 1500 bytes. A byte is a reference to computer memory, and when you're first learning all of these concepts, the simplest way to think of a byte is one letter in a sentence. So if you send the phrase, "Hi, my name is Derek," that's 13 bytes, one for each letter, including the spaces, including apostrophes, and including the period. If you don't have a minimum amount of information to send, most computers fill the existing space with just zeros. After the payload data, there is a field that is tagged onto the end of the Ethernet frame, which is the CRC. This is called the cyclic redundancy check. The CRC is used as a sort of fingerprint to verify the contents of the payload. Sometimes electrical interference can change the bits on the wire before they arrive at the target destination. The CRC and the payload do not match, then the frame is going to be discarded and it will need to be retransmitted from the source. So while I'm describing frames in the context of switch communication, you may have heard the word packet used. Packets are in reference to two different things. There's an IP packet, which is a layer 3 protocol known as Internet Protocol or TCP/IP, which I'll be discussing shortly in another video. And there's also the concept of an Ethernet packet. There is a slight difference between packets and frames. Packets are what frames are contained in. Packets contain timing data, delimiter data for starting and ending of the Ethernet frame inside. An important term that we're going to be revisiting frequently is that of encapsulation. When you have a packet, it encapsulates a frame, and then a frame encapsulates a payload. Within the payload will be even more encapsulation, which we'll get into somewhat more in other videos. When your network interface card receives a packet from the switch, it strips the front header and the tail and passes only the frame itself towards the operating system. The concept of a MAC address, a network interface card, and a MAC address table are the basic building blocks of a local area network, which is a group of computers that are just connected to switches. If your local area network is not big enough because you do not have enough switch ports to work with, then you can patch one switch into another switch. It's important to note in the beginning when you're first learning, it doesn't matter where you patch a switch into another switch. You can patch it into any of the available ports and you will have created a bigger network doing this. If you still don't have enough, you could do it again. By adding the 24-port switch, I've made a much bigger network. Now, when I patch switches into each other and expand the size of my network, does this unit trade MAC addresses with its neighbor? The answer is no. These devices do not really know about each other and they don't communicate with each other the way that a computer might. Each switch will individually build its own MAC address table based upon the packets that roll through its switching ports. If you were to somehow look inside the memory of each of these switches, you would see that their MAC address tables are actually quite different. And they don't really know where certain MAC addresses are plugged in, other than they know, say, on this port here, where I have two switches plugged in a chain, there might be dozens of MAC addresses showing in the table on that single port. Any frame destined for any of those MAC addresses go to that port. They then reach the next switch, and that switch compares any received frames against its MAC address table and forwards it wherever it thinks the targets are. Whenever the switch does not have a destination MAC address in its MAC address table, it forwards that frame to every single port. If it then sees an answer come back, it will build its MAC address table from that broadcast. Future frames that are sent are then sent singly, or what's called Unicast, directly to that particular port. You'll notice so far in this video that I haven't referenced IP addresses. As a general rule, switches don't know anything about IP addresses. They operate at a lower level than your computer and your router. Switches are just able to pass frames around. They don't know anything about the contents, which is where your IP information is actually contained. It's in the payload of an Ethernet frame. That being said, there are two kinds of switches that you'll primarily encounter in your experiences out there. One is the unmanaged switch, which is this little guy, and the other kind is a managed switch, which is this one that it's stacked on. A managed switch has an interface that you can log into to monitor its overall status. And very frequently, these things keep track of the IP addresses that they see coming and going in the different payloads. However, even when a switch understands that IP addresses are passing between its ports, it doesn't use them in making any determinations on which port to forward an Ethernet frame through. That's something that routers do and computers do, but switches will blindly pass traffic as long as the frames are formatted correctly. I'll expand greatly on what you can use a managed switch for in a future video. But for now, when you first get a managed switch out of a box, it doesn't act any differently than an unmanaged switch. You plug in things anywhere you want and you expand your network with it. They pass frames between each other and it's that simple. Okay, students, this is a hands-on lab. I don't have a script, so I'm just going to kind of wing it as I'm talking, but I want to cover some important topics when it comes to interacting with your switches. If you don't have switches at home or at school or at work, I want you to borrow them from anyone you know. You always want to have a couple of these devices laying around so that you can do some testing. So if you want to follow along, grab up some switches from wherever you've got them. I also have a pair of laptops that I'm going to use for part of my demonstration. We'll get a little bit more into the commands that I'm typing and how I'm checking if they're in communication in a future video. This particular lab is about the switches themselves. So let's cover one of the most important things. Connecting the switches to each other, as I've said earlier in this video, expands your network. So an example here is this is my first switch. I'm going to plug in an RJ45. I'm going to patch that into the next switch. The first thing you should see in a lab environment is a green link light, just like I've got right here. Now, where do we go from there? Could I go from a second one to a third one? Yes, I can. So let's do that. We got ourselves more link lights. So now I've got 3 switches plugged into each other. Can we keep going? Yes, we can. So let's do that. Let's make a bigger network. Okay, now we're really getting somewhere. We got a nice sized lab of lots of switches creating a bigger and bigger network. Now, can I go even bigger? Yes. I'll take the last switch that I've just done and I'll plug in to this switch. This switch has an interesting property in that it can be powered up just by the Ethernet cord. So that switch delivers enough electric power to bring the circuitry online as well as passing information. This is called power over Ethernet. I'll get into this a little bit more in another video. It just happens to be a switch that I had laying around, which helps me do this demo. So if you look, all our switches are plugged from this one to this one to this one to this one to this one. When you've got things lined up in series like this, this is called daisy chaining. And if you were to draw this network on a piece of paper, what you would be drawing is called a bus. So what's the words I'm trying to say? What we call the layout of all your switch devices as they physically are and as they are on paper, we call those a topology. The paper or theoretical design is the logical topology, and the way they're physically laid out on the table is the physical topology. Sometimes they're the same, sometimes they're different. In this situation, I've made a bus. A bus goes from one device to the next device to the next device. Very easy to understand. Now, if I take one of my laptops, I've got my MacBook. My MacBook does not have an Ethernet NIC, so I've got a USB to Ethernet adapter to give me that NIC. If I plug that MacBook into the first switch, I now am part of this large network on my laptop number 1. Now, laptop number 2 is a Dell Latitude, and I'll put that over here. This one does have an integrated NIC already on the motherboard, so I don't need a USB to Ethernet adapter for this laptop. But I do have one just in case. So this actually is going to be an interesting part of our lab. But let's start at the beginning. First laptop in first switch, second laptop in last switch. So let's just confirm that we've got link lights where we expect to have them. So I've got link light green, link light green. I'm going to wake up the computer, and I'm just going to see if I can communicate. What did I type? You never know with me. I'm going to see if I can communicate with my neighboring computer at the end of the chain. Okay, so what I'm doing is I'm issuing a ping command, which is a command that tests network reachability between 2 computers. I'll get into this a lot more in another video where I go over all of the command line troubleshooting tools that you might need to use when you're doing a lab. But as your very first, a ping just goes from one computer to the other computer. The Ethernet frame that I'm sending from my NIC is converted into destination, source, the payload, which is the ping command, and then there is a checksum at the end to make sure that we didn't lose any of our electrical transmission along this pathway. What happens initially on the very first ping is this device sends a broadcast because it does not yet know what is the MAC address of the other laptop. So there is a broadcast that goes out, which hits this switch. This switch's MAC address table, when we first powered all this together, was empty. So it doesn't know where that switch is, or where that laptop is at the end of my bus. So what does this switch do when it receives a frame and it doesn't know where to send it? The switch itself sends a broadcast. Where does the broadcast go? Only to the ones with a link light on it. So this is my laptop. This is my only other live port. So the broadcast goes down the bus to the second switch. The second switch also has a blank MAC address table because we've just got started. The very first ping, everybody's table is blank. So this switch does also a broadcast down the only other live port that it has, which is towards this. The process repeats each time till we get to the very last switch, and the very last switch sends a broadcast, but finally the last lit port reaches the laptop, which then answers. When the answer comes through, the MAC address table starts to build. This switch now knows where the MAC address of this laptop is. This switch also knows where the MAC address of this laptop is. It's on this port. So target and source. MAC address table starts to build up. So because it knows and it's gotten a response from this laptop, to send the response back to my laptop over here, the first one, it forwards it Unicast directly down this port. It now knows where to send things. Same thing happens over here. There's an inbound frame from that switch, and this switch builds its MAC address table from that information. Then it sends it Unicast down that port. The process repeats all the way down the bus until it reaches my first laptop. We now have two-way communication. So there are some questions that people frequently ask me. How many switches can we connect in a bus format like this, in series, or how many can we daisy chain? There's no practical limit. There's only the limit of common sense. Imagine how big your office would be if I had one of these all over the place and I was just sort of going from room to room with it. If there was ever a problem with one of these switches, oops, we lost power. We've broken the bus. Now information only goes to these two switches here. Can't reach my target laptop. My target laptop is now isolated from the rest of the network. We've accidentally, by unplugging the middle switch, created two independent LANs. We didn't mean for that to happen. Now, we have it right here on our desk. They're easy to find. They're easy to fix, plug, put it right back. I lost communication, as you can see on the screen, but communication will be restored once the switch boots up. Takes it only a moment or two, but once we have link lights come back on, we'll start to see communication restored. So if you think of how easy this is in a lab to screw up when they're right next to each other, imagine how hard it is in a very large warehouse, office, or even a big house, or your school, wherever you're setting this up and testing it. What you're going to see happen is a big chunk of the network will go offline, and you'll be crawling all over the place looking for all your little switches. Which one of you did this to me? Which one of you went offline and screwed this thing up? Well, I got so carried away, the laptop fell asleep and stopped responding to the ping. So that's something you should also think about, is don't let your lab computers go into energy saving mode. That was a mistake on my part. Let's not do that again. Now, you're going to see a lot of comments that the way that I've got this plugged in is completely wrong. And that's an accurate criticism. Should I have installed them together in this fashion? Answer is no. And would I do this in the field? Answer is no. So I'm going to unplug everything and I'm going to start over. We'll just speed up. Okay, let's start over and let's put the switches together in a different topology. So the alternative to the bus is the star topology. And with a star topology, one of your switches is in the center and the others are leaves, if you will, if you imagine it like a tree. So I'll start with my center switch, and then I plug in each of my neighbors to the center only. Yellow. So with the center switch, we're essentially creating a single point of failure. We can lose the leafs, but the rest of the network continues to operate. So whichever laptop I've got here, if I unplug the power to that leaf switch or one of the branches of my star, we'll essentially just lose that spoke of the network, but we'll be able to continue operating in all other departments. So there won't be a chain reaction of network loss the way there is when we're doing a bus topology. So whenever possible, I try to use the star, and that would be in a rack where you've got a lot of smaller switches out there that you're distributing connections to. In the rack would be the central rack, network cabinet. Let me be more specific. In the network cabinet, there'd be a central distribution switch that spiders out to all of the sub switches that then distribute connections to, say, a classroom or a department or a room in your house even. So this is generally considered superior due to the resiliency. Now, if you lose your central switch, it's over. They're all dead, but it's just as bad as when you have a bus and you lose any of your switches in the bus. Unless it's the very last switch in your bus, any switch loss along the pathway is going to be pretty devastating. So it's just as likely that, let's say in a bus environment, if you lose even one switch, it's almost always fatal, where in a star environment, losing only the central switch will be fatal. So it's a little bit more resilient. Now, can you mix and match a star and a bus? Yes. In fact, I don't have a choice because you'll notice I didn't plug in this last one. This last one needs power delivered to it from a power-capable switch. This middle one that I chose does not offer power. So there's nothing stopping me from patching in to one of the leaf switches and getting power that way. And I've created a star, and on one of the spokes, I've started building a bus. There's no reason that you cannot do that. In fact, you should try every single configuration that you can think of when you're building your lab, because you want to know how your switches interact with each other. And you also want to know, it fell asleep again, look at me. Can't take me anywhere. You also want to know whether or not there's a gotcha or a quirk or something weird about the switch hardware that you've got in front of you. Sometimes when you mix brands together, there's odd behaviors. So I like to try everything that I can try all at once in order to, make sure that I'm aware of all the little steps that the average user wouldn't know about. I'll know it because I like this hardware and I always pick it and I know the funny little things that it does. That's a big part of doing your lab, is learning the quirks of hardware. So let me bring up some unusual situations. I have a laptop here that has its own integrated NIC, and I can plug it in anywhere along the chain. And we should, in theory, start to get our answer now that I have it attached. What if I attached this USB to Ethernet NIC to this laptop that already has a NIC, right? And I then patch it in somewhere else? I could patch it in to the same switch or a completely different switch. What if I had more USB to Ethernet? What if I had 2 on my Mac? What if I had 3 on my PC? What becomes of the internet traffic that's going between them, or network traffic? Is anything bad happening in this scenario? The answer is no. This is okay to do, and this doesn't hurt anything. Your computers are smart enough to pick a primary interface, usually the fastest one. So if you've got wireless and wired, most laptops will use the wired if it's available because it is faster. However, you can set priority and other routing rules so that under certain conditions, different NICs get used. I'm going to build a lab based around that in a future video. The other thing, let me unplug this NIC. The other thing that you want to try out when you get the opportunity is if you create connectivity between two laptops in your lab, you might want to try doing something what is called a loop. So if you connect your last switch, or really any switch, back to the first, or you connect your switches in such a way that you've broken the topology, it's no longer a bus, it goes all the way back to the beginning, or you've looped just two of them, or if you've got a star, if you go from one spoke to the other spoke, that will create a loop. What becomes of your network then? Do you lose connectivity? Does anything change? Try it out when it comes to, say, sharing files over the network. We'll get there a little later in the other videos. I'll try different activities and I'll try it with or without a loop so that you can see the effect that it has. Sometimes plugging a switch into another switch and then back again is devastating. You won't be able to do any network operation. And if you think about why would that be, broadcast packets that go out, or frames, broadcast frames, go in a circle. And there's nothing in the Ethernet format that says when a frame should be discarded. They don't have a certain lifespan or anything like that. So they'll continue traveling in a circle around the network over and over and over again. And then the next broadcast gets added and the next gets added, so that over a short period of time, millions of broadcasts are just pointlessly replicated in a circle. And eventually they wear out the integrated electronics within these switches. Their memory is full. Their transmitters are doing everything they can, just sending useless information that they've already seen and received that has no real destination. So in a scenario like that, having a loop can be absolutely deadly. And look, I lost him again. Wake up. So it's not uncommon to lose network connectivity or have intermittent network connectivity based around accidental loops. And users can do this really easily if you place a lot of small switches all under their desks. It doesn't take much for them to cross-connect back into themselves on accident. And then your whole network, everything in your star, everything in your bus, wrecked. Okay, that's a lot for one video. That's a pretty good lab. We'll be coming back and setting up more labs for more, advanced scenarios. Each time I bring up a new topic, I'm going to set up a lab like this. Remember, you have to do it with your own hands. If you're just theory only, then you don't really know. Always try to do the thing that you've read about or that you've seen in a video like this one. If you don't try it, you won't know the little pitfalls. And those will be the ones that kill you in the field. Okay, friends, I'm going to wrap it up there because I want to move on to talking about IP addresses, which are the next logical thing to be discussing. And most of you are probably not that interested in layer 2 stuff or what switches are doing. They're kind of simple devices that we take for granted, and that's okay. Now we're going to move on to something more advanced. But I want to just quickly recap what we discussed here in this chapter. Switches' job is to pass Ethernet frames between devices. When they don't know where to send a frame, they send a broadcast. And with the results of all the message passing that they get back and forth, they build a MAC address table. MAC addresses being the serial numbers of each of your network interface cards in each of your computers. I really appreciate that you stuck it out with me. I know it's some dry material. It'll get more fun as we learn more and set up bigger labs. I'll see you again soon in the next one. Thank you.